quantum theory, the laws that govern the very small particles, electrons and so on, and general relativity. Stephen is looking for a single theory that explains all the forces in the universe.
In the vast expanse of the cosmos, where mysteries abound and the fabric of space conceals secrets beyond imagination, there lies a phenomenon that challenges our understanding of reality. Are cosmic strings the enigmatic cracks in the universe, unseen threads weaving through the cosmic tapestry? In this episode, we'll unravel the suspenseful tale of these cosmic anomalies, exploring their origins, characteristics, and the profound impact they may hold on the very fabric of our existence. Buckle up as we embark on a cosmic journey, delving into the question, are cosmic strings cracks in the universe? This is Reveal the Mystery. If you are curious to learn mysteries of the world, space, and beyond, consider subscribing. Higgs field. A quantum field is like a numerical characteristic present in space. It can change around a specific number, and these changes turn into particles when they move through space. The field's numerical part is called its strength, depending on the field's energy, often in complicated ways. When there are no particles, the field settles to the closest energy level, known as the vacuum state. In the early universe, the Higgs field reacted to energy changes with a single value. Even in this state, a lot of energy remained. The potential curve of the Higgs field, influenced by temperature, developed bumps as the universe expanded. The Higgs field has two strengths, and the new minimum took a ring-like shape around the original, resembling festive headwear. Suddenly, the Higgs field in the universe had more energy than needed, like a ball on a hill. A slight disturbance could make it roll in a random direction, causing vacuum decay. This made the Higgs field move towards a new state. Points in the field influenced each other, converging to the same value, similar to magnetic dipoles aligning. Vacuum decay created bubbles of lower energy that expanded quickly. Merging bubbles erased the old high-energy state, forming strings in the Higgs field. The vacuum decay happened randomly, assigning a phase angle to each point, defining the Higgs field's two components. The vortex. Imagine an area where things are changing, like the air around you. In this changing place, the way things are turning or moving would be pretty similar because everything is pulled towards where it all began. But if you have different pockets of change, they might be turning in different ways. When these pockets come together, the turning part at the edge tries to match up. This creates a pattern with the turning part slowly changing across the whole space. However, if many pockets join with different turning ways, the easiest way for them to line up is to smoothly change around a loop, like turning around a point twice. This creates a tangle in the loop where things can't match up. The center of that tangle has to take on an older value instead of the new one. It's like a leftover from an old high-energy time that still hangs around in the present universe. This twisty structure is called a vortex. We see flat versions of this everywhere, from cyclones to the way hair swirls on your head. In a real three-dimensional space, this kind of twisty thing appears as a shape around a middle line. That middle line is what we call a cosmic string. There might be other twisty things too, like a point without any size, which could be a magnetic monopole. Quantum fields. Reality displays fractures through universe-spanning filaments formed by ancient Big Bang energy known as cosmic strings. These subatomic entities, arising from topological defects in quantum fields, possess minuscule dimensions but carry significant mass, hurtling through space at nearly the speed of light. Despite their mysterious nature, evidence suggests their probable existence. Understanding cosmic strings involves exploring phase transitions in quantum fields, akin to freezing an entire universe like a flawed ice cube. In the early universe's extreme temperatures, a phase transition occurred in the foundational quantum fields, drastically altering particle behavior. The intricate structure of the contemporary force-carrying field, responsible for electromagnetic and nuclear forces, simplifies at high temperatures, analogous to ice crystal dissolution. In the immediate aftermath of the Big Bang, most vibration modes of quantum fields likely vanished, unifying force-carrying fields into a singular force. This phenomenon, observed in electromagnetic and weak nuclear forces, is likely true for the strong nuclear force and the Higgs field. Contrary to popular belief, the Higgs field and boson, besides providing particle masses, constitute a fifth fundamental force. This force arises from the same field structure as other non-gravitational forces and manifests as cosmic strings during field solidification. Cosmic strings. We've successfully captured the quantum fields in the early stages of the universe, giving rise to cosmic strings. But what exactly are they, and what role do they play? These turning points, or phase angles, refer to a line, tightening the loops around them. Despite their subatomic size, about 1/10 trillionth the width of a proton, these strings carry immense energy, equivalent to the mass of the planet Mars for every 100 meters of length. Extending across the universe, these strings originated from the distance light could travel during the vacuum's evolution. As the universe expanded, these strings stretched to the size of the observable universe. Multiple starting points in various regions may have led to a network of dozens of cosmic strings. Unlike frozen water forming ice, cosmic strings exhibit movement and vibration, traveling at almost the speed of light due to incredible tension. Collisions between different strings or sections often occur, resulting in two possible outcomes. They pass through each other or switch places, known as intercommutation. A straight string collision can cut out a loop, which, if intersecting with itself, forms smaller loops. Despite this, larger loops persist and multiply over time, spreading across the universe. Following intercommutation, pairs of kinks form and speed away from each other along the string, emitting gravitational waves due to their significant mass. This causes cosmic strings to lose energy, gradually fading away. Ultimately, they vanish as the Higgs field evens out across the string. Smaller loops disappear faster, accelerating the overall process of cosmic string disappearance. Locating cosmic strings. If we believe cosmic strings are real, how can we find them? Let's start with gravitational waves. These waves should be like beams emitted in the direction the string is moving, possibly causing flashes as they pass over our gravitational wave observatories. Current detectors like LIGO might not be good enough, but future ones like LISA could do the job. Another way involves the pulsar timing array, which spots irregularities in the regular flashes of light from pulsars to find gravitational waves. It might also catch signals from kinks in cosmic strings. The second method uses gravitational lensing. This happens when gravity warps space and bends light from faraway sources. If a big object like a cosmic string is between us and a distant light source, it can make the light bend toward it, maybe creating split images or even a chain of splits in the sky. So far, no such chain has been found, but upcoming sky surveys might change that. If we do find a cosmic string, there's one more thing to figure out. Is it a regular cosmic string or a cosmic superstring? You might have heard about string theory, a kind of theory that uses one-dimensional strings. But these theoretical strings are super tiny, not like the much bigger cosmic strings we're talking about. Cosmic superstrings. The universe may have ingeniously intertwined the two types. During the early universe's inflationary epoch, exceptionally tiny entities like strings from string theory could have expanded to cosmic proportions. These magnified strings, now termed cosmic superstrings, frustratingly mimic the behaviors of regular cosmic strings, exhibiting traits such as gravitational waves and lensing. Notably, when regular cosmic strings collide, they usually intercommute by passing through each other. Conversely, cosmic superstrings are more inclined to pass straight through without frequent chopping. They can also form junctions, merging two different superstring types into a connected string. Identifying such junctions could differentiate them. If a superstring junction induces gravitational lensing, it may create a distinct six-part image, potentially supporting string theory. Additionally, cosmic superstrings decay more slowly than their counterparts, contributing to a potentially stronger gravitational wave background with a different pattern. We haven't discovered cosmic strings or superstrings yet. However, our investigations have set limits on the possible tensions and energies these entities can have. It's crucial to continue our search because there's a good chance that the universe is filled with traces of its early vacuum. If we manage to find one, who knows what valuable insights we might gain.